It's time to start. So do you have any questions regarding the labs, tests, homeworks, last lectures, anything? No question? So today's lecture will be all about uncertainty and about like thinking, reasoning about uncertainty and making some decisions. It's heavily based on the Artificial Intelligence Modern Approach book that we recommended for this course, chapters 13 and 14, and also based on many other courses which are following the same chapter. So I was taking inspiration from these other lectures, and you can look at those to see how others are trying to explain it. And we'll be talking about rational agents, right? In AI, the idea is mostly to create rational agents that will act in some environment. And we are already talking about that in the multi-embedded problems, that when you want to make a rational decision, you need to estimate the expected utility of different outcomes that might happen, and then you need to estimate the probability of those outcomes, and then you just multiply this and you pick the action that leads to the highest expected utility, right? This is what we kind of expect from a rational agent to do. And in order to formalize it, to implement it in a computer, we need two kind of fields, two research fields. One is utility theory, which is talking about how to measure preferences among different outcomes, right? Like the very natural way is to just think of some numbers, like if there is a higher number, higher reward, you prefer it more. But this is more complex, like what preferences you can have, how to aggregate preferences and so on. And there is utility theory for that. We are not going to dive deeper into utility theory. We'll just assume that we have these numerical values which express how much we want certain outcome. And the other part is the probability theory, right? We need to estimate in certain domain, in certain situation, like how much we expect that each of those outcomes will happen, right? And for that, we need probability theory, and we'll be talking much more about that in this lecture, like how to model environments, worlds, situations, how to take into account evidence in order to update your beliefs about the probability that different things might happen. Like a very simple tool to study this expected utility and probability are lotteries. We have seen such lotteries in multi-embedded scenario, where you give people or the agent some options of getting some outcome with some probability, another outcome with another probability, and you can study like who prefers what. But we just want the pure utility and pure probability. Okay. So where do we see in AI applications this kind of reasoning about outcomes and probabilities? So very often, probably the main domain is the medical domain, like medical diagnosis. We already had that with mycin in the past, but people are still interested in it. So how does it look like? You get a patient, the patient tells you pretty much for free, very cheaply, some symptoms. You can measure some temperature and whatever, and then you have a range of tests you can perform on those patients. And every test has some specificity, some accuracy, and so on. So you can think of COVID. You probably remember that, right? So you have a patient, you can measure his temperature. You will say, okay, it's a COVID pandemic. I have a patient who is like has full nose, doesn't smell, and has temperature. So probably he has COVID, right? But you are not certain. So then you can give him the antigen test. And the antigen test is cheap, but it's not very reliable. So you know that if the test is positive, then you have some probability that he actually has a COVID. If you want to be more sure, you can give him the PCR test, which is more expensive, but more precise, right? So we have different types of observations, different types of evidence that you can gather. You would pay different amount of money for each of that, and then you will have some final probability that something is true or that you should do some decision. Similar in IT support, if you call to a support, they would have a graph. Something is wrong with your computer. Again, they will ask you questions, maybe ask you to like restart and call again. Everything is some kind of border. Everything gives them some evidence, and you can work with this evidence. Same in car repairs or whatever. So diagnosis is one big thing where you need to like reason about uncertainty in some systematic way. But there are other topics. Like this is not exhaustive list for sure, but there are just some examples. So robotic localization. If you have anything in common with robotics, or you were thinking about it more, you know that everything is super uncertain there. Like any sensor you can have, for example, about your location, is noisy, right? So if you measure by rangefinder that board is, I don't know, 3.5 meters in front of me, and maybe it's 320, maybe it's 370, like who knows? There is some probability distributions that is measuring like how imprecise your sensor is. When you are trying to go 1 meter, you are moving your wheels, but the wheels can slip. You can count how many times the wheels turned, but you cannot really know like whether they slipped, whether there was something on it that you had to go over, or something. You will have some kind of uncertainty. So if you want to localize your robot precisely, again, it's useful to have some probability distribution where you could be, and with every single new observation, with every new like sensory measurement, you want to incorporate that into your belief about where you might be. Similar natural language processing, again, many applications of this probabilistic reasoning. Probably one of the most famous one is spam filtering that like has been done this way for at least 30 years, and now in most systems it's still done this way, where you have some words which appear in clean emails and some words which appear in spam emails, and those are slightly different. So every word is a piece of evidence. Like if you have Viagra in the email, then it's less likely to be a regular email. If you have some like complex scientific terminology or whatever, like legal jargon or something that is much more connected to workplace, then it's much more likely that it's a regular email than a spam email. And again, like counting all the words, counting all the evidence to your outcome can give you a spam filter. Last thing that I definitely wanted to mention is large language models. Like that's a huge thing now. And large language models are, I'll be talking much more about that in a couple of weeks, are basically a probability distribution, right? They are probability of the next token, like you can think of word, given some sequence of previous words, right? So you want to represent this probability, you want to compute with this probability. So again, knowing how to work with probability distributions, how to represent them, what properties they have, is super important even in this use case. Okay. Any questions? If not, then in this lecture, we will briefly remind ourselves how probability works, what objects we have in discrete probability distributions and how to work with them. Then we will motivate Bayesian networks, which are compact representations of these joint probability distributions, which allow us to store them in smaller space and reason about them and like run some algorithms on them faster than on the just raw probability distribution, and that they have some other advantages as well. We will talk about single algorithm to actually perform inference in Bayesian networks and to like add evidence and see how different outcomes will change, and mention some special structures of Bayesian networks which are studied separately. And at the end, hopefully, I'll have enough time to talk about causality and the difference between causality and correlation, and how that relates to Bayesian networks and causal networks. So first, random variable. You have seen that we can have a random variable sunshine, which will usually denote them by these capital letters, which can have two different values, like either no sunshine or there is sunshine, right? Rain, no rain, rain. So that would be Boolean variables. We can have some multi-valued variables like dice throw of a dice would be D, and again the values that it can get is 1 to 6. Again, like this is, I assume this is something you know, so we are just reminding it. If not, stop me and I'll try to explain it somehow quickly. Then you can have a joint probability distribution, which tells you probability of all the combinations of different variables, right? So if you have a joint probability distribution of sunshine and rain, then you can have no sunshine and no rain with probability 20%. You can have no sunshine and rain with probability 8%, sunshine and no rain 70%, and sunshine and rain 2%. Right? You can draw it in this kind of a table. And generally, if you just write a comma here, that means and, right? Like sunshine and at the same time rain. Then if you have a joint probability distribution, then you can compute a marginal probability distribution based on that. So you can basically sum out some of those variables you don't care about. So if you just want to know what is the probability of sunshine and you don't care about the rain, you can sum up all the values for sunshine false, which would be these two. It's this result. You can sum up all the values for sunshine true. That would be some of these. That's this result, right? So that's called marginalization, and it's an important operation with these probability distributions. Another similar operation is, or similar distribution. So that's actually an important difference that many people don't get, even in the test. So this is joint probability distribution, saying what happens if, like, or what is the probability that this and this is true. And then there is a different distribution, which is called conditional distribution, which is what happens with some variable given we put some other value of that variable. Like given we observe some other value of the variable, right? Like if we observe that there is raining, what is the probability that it will be sunshine? And how do you compute that? It's easy. So you look only at those that follow, like in the joint probability, the ones that where the condition is satisfied. So it's this row and this row. Yeah, it's raining true. And you normalize that, right? And that's conditional probability. What is the probability of sunshine given that raining is true? Does it make sense? Is it all like well known or uncertainties? Okay. Good. So this is how you represent the distributions, and then you have some basic rules how you can compute with probability distributions and probabilities in general. So one thing is that, of course, like sum of all probabilities of valuations of certain variable should sum to 1. And then you have this super important rule, which is called product rule, which is just saying that the probability that A and B happens is equal to probability that A happens given B. So if we observe B, what is the probability that A happens? Times the probability of B. Like this is a super fundamental rule of probability that can be used, and we will use it the whole lecture for many, many things. And one thing that you can do with it is to derive the Bayes rule, right? So you probably will trust me that there is some commutativity. So probability that A and B will happen is the same as probability that B and AA will happen, right? If you believe that, you can apply the chain rule, the product rule, on both of those, on left side and right side, and then you will just move this probability of B down, and you have Bayes rule. And a Bayes rule is this super, super fundamental thing. We'll see it working many, many times. But it tells you how to compute probability of some event, some outcome, given that you have observed some evidence. So probability that I have COVID, given my PCR test is positive, from probability that my PCR test is positive when I have COVID, which is much easier to compute, right? You can run clinical trials, you can take many, many people who have COVID, you will measure how often their test is positive, right? So getting this is much easier than getting this other value, which is like probability that I have COVID, because it's very hard to find out. You can use very expensive things to find out here, and then measure how good the test is. Probability A is just the a priori probability. You need to take that into account. Like if there is a pandemic, there is much higher chance that you have COVID than like 20 years ago. Like there will be very, very little chance that you have COVID, right? And probability of B is probability that the test will be positive, right, on its own. So this is the Bayes rule. Any questions? We'll see it working many times in the future. Okay, so if we remember these basic tools, we can do some basic probabilistic inference. So what do I mean by inference or reasoning? It's trying to get some answers based on the model of the situation, right? That's what we will do. And in this case, the model of the situation is just this joint probability table. What does it mean? Like, can you read a table like this? It's a 3D table. So I'll just go through how it works. So you have variables. Here you have 3 different variables. One variable is whether you have toothache or not, like whether your teeth ache or not, whether you have a cavity in your teeth, and whether this kind of hook that the dentist is using to like probe your teeth will catch in the tooth or not, right? Whether like when he puts the hook into the tooth, whether it stays there or not, right? So that's the catch variable. And now, if we have this field, for example, it says that you have toothache, the hook didn't catch, but you still have cavity, right? That's the meaning of this field. If I think about this field, it means that you don't have toothache, you don't have cavity, but the hook still caught somewhere in between the teeth, probably. Does it make sense what this table means? It just gives you all combinations of all variables, and for each of them, it will give you a value, and that's the probability that all that combination is true or like false if there is this negation. Okay, once we have this, we can start computing some new probabilities. So for example, we can be interested in this probability that you have cavity when your teeth ache, right? We don't have that explicitly anywhere in the table, but we know that it's probability of, from the Bayes rule, it's probability of cavity given ache times probability of ache, and that's this joint probability of cavity and ache, right? So we can just look into the table and see what is the probability of cavity and toothache, and marginalize out the catch variable, right? So you have cavity all here, you have toothache here, right? So this is what you care about, and you don't care about the catch, so you will just sum these two, and that's what we do here. Right? So that's probability of cavity and toothache. And we need to divide by probability of toothache. So how do we find it in this table? Again, like we have toothache here. We don't care about the cavity and about the catch. So we just sum over everything we don't care about. So we sum all of these four here, and the result is 0.6, so 60%. If you have a toothache, there is 60% chance that you have a cavity. Okay. We can compute the probability non-cavity toothache very similar way. We will take non-cavity and toothache. Again, non-cavity and toothache will be this. We sum it, we normalize it, we divide it by the same thing, and we have 0.4. Of course, we know that probabilities sum to 1, so very often what we do is we would forget about these denominators, we would compute just denominators and normalize. Right, and then you will find out that the denominator is here 0.12, and here is 0.808, and if you normalize it, you will also get 60/40. Okay, so I'm claiming that if you have this kind of joint probability distribution, telling you relationships, probabilities of all combinations of all variables in your system, you can make a lot of inference like this. You can basically find out what is the probability of any variable given any kind of evidence in that system. Do you believe me, or are there any doubts? Okay. So where is the catch? Just imagine that you want to apply it to realistic situation. Would that be easy, hard? Let's say we don't have this toy problem, we have real dental diagnosis, and you have your sex, you have your age, you have your what you eat, you have I don't know, another 50 different variables that we want to take into account, which somehow influences whether you have a cavity or not. Would there be any problem, or can we just like make this table and compute the probabilities like this based on whatever, right? And you give me your anamnesis, you give me 10 of values of those variables, and I want to compute the probability that you have cavity. Are there any problems? Mm-hmm. Exactly. That's the point, right? Like this table grows exponentially with the number of variables, right? So if we have 50 binary variables, then the size of the table is 2 to the power of 50. If they are not binary, if you have different values, it's even worse. And like 2 to the 50, it's just insane number, right? Like you will never fit any table like that into computer. And that's just part of the problem. Like you cannot fit it into the computer. If you could fit it into the computer, just like summing over all the variables you don't care about would take you forever. So you would never actually finish your computation. And that's still not the biggest problem, right? The biggest problem is where do you get all those numbers, right? You need 2 to the power of 50 different numbers to measure somehow and put into that table. So it probably like wouldn't work that way. Okay, and that's exactly the motivation of Bayesian networks. Like Bayesian networks are trying to work with these domains of large tens of variables in some more efficient way. Like I wouldn't say really efficient way because it's just not possible, but in a much more efficient way. And what it uses to do it is probabilistic independence, right? If you know that some of those variables are independent, you can factorize the problem. You can try to make several smaller probability distributions in such a way that you will still be able to compute all the probabilities based on all the evidence. So if you imagine that you take into account other things like weather, for example, into your model, and the weather can be cloudy, sunny, rain or snow, then your table would grow to 32 different fields. But if we know that, and we know from the chain rule, right, from the product rule, that the probability of cavity 2-day catch weather, like the table we are trying to store, we can store it as two different tables. If we assume, I don't know why the buttons have swapped. If this is X, and this triple is Y, right? Then we can say that this is probability of X given Y times probability of Y, if we think about each triple. So we can use the product rule, and we can rewrite the larger table using two smaller tables. Or in this case, different tables, like this is still rather large. But then we can use probabilistic independence. So what is probabilistic independence? I should have spoken about that at the beginning as well. Do we know when A and B are independent? I probably speak about it here later. So they are independent if they don't influence each other. If like the intuition is, if we learn the value of one, we don't learn anything about the value of the second, right? That means that they are independent. And in this case, like if we learn that you have cavity, how does it influence the probability that it's sunny? Not much, right? Or that you have a toothache, how does it influence the probability that it's raining? Not too much. So if we assume that probability of weather is the same as probability of weather given all these things we assume don't matter for the weather, then we can represent the whole information of this table in just the probability of weather, right? And then we can replace the table here, and instead of this large table which has 32 fields, we will store this probability table as this probability table we had before times probability of weather. And that gives us all the information we need to model the domain. And the overall representation is just 12 fields, right? Because this is 8 and this is 4. Does it make sense? Like this is the very kind of key idea behind Bayesian networks and graphical models in general. Like you can represent larger probability distribution by multiplying smaller probability distributions, and then you can use independence to simplify some of them and store just the simplified things which should still contain all the information. So this is absolute independence, which is rarely the truth, because even this assumption doesn't hold. Does anyone see why? Why, if I observe that your teeth ache, it might change the probability of what the weather is? There are some metal sensitive people, right? So there's like your grandma might always have teeth ache when it's going to be raining. And then if you find out that your grandma's teeth ache, you increase a little bit the probability that it will be raining outside, right? So there is some connection, and always there are some connections, but often the connections are so weak that it's more efficient just to ignore them and model the domain without it, so that you can basically compute it. Okay. Complete probabilistic independence is quite rare. That's why we often need to assume conditional independence. What does it mean? Conditional independence means like that your variable is not influenced by some other variable anymore, by observing the other variable anymore, if you know values of some other variables. So on a concrete example here, the probability that the hook of the doctor will catch in your tooth depends on toothache, right? Because if your teeth ache, it's more probable that you have cavity, it's more probable that the hook will catch, right? But if I already know that you have cavity, then it doesn't matter whether your teeth ache or not, right? If I have if I know that you have cavity, the probability that the hook will catch is the same whether your teeth ache or not, right? Like because the hook catches in the cavity. So I cannot say that the catch and toothache are probabilistically independent, but I can say that they are independent given the cavity. Does it make sense? So X and Y are independent given Z if one of these following happens. Like this was this first one, where X was the catch, Y was the toothache, and Z was the cavity, right? So if probability of X given Y and Z is the same as probability X given Z, like for just without the conditional, I didn't have it there, but if probability A and B is probability of A times probability of B, A and B are completely independent, right? Here we have the same variant for the conditional independence. So if it holds that probability X and Y given Z is the same as probability X given Z and probability Y given Z, then X and Y are independent. And you can have this swapped. So you can even say probability of Y given X and Z equals probability Y given Z. That also means that X and Y are conditionally independent given Z. Right? So if I know the value of Z, knowing X doesn't help me change or update my belief about Y. That means that X and Y are conditionally independent given Z. Does it make sense? Okay. And now we can use even the conditional independence. So we can use the product rule iteratively, right? I was saying that the product rule is probability of X, Y is probability of X given Y times probability of Y. But this Y, as we had in the example, can be a complex variable, a combination of many different things. So I can say probability of A, B, C, D, for example, is probability of A given B, C, D times probability of B, C, D, right? That's just application of the product rule. But I can continue. I can use the product rule again and apply it on this, right? So I can say that it's probability of B given CD times probability CD. And I can go on, right? So C given D times probability D. So any joint probability distribution, you can always rewrite as this sequence of a linear number of conditional probability tables, where this is already, like this is the same size basically, but these are already smaller. Yeah? And now you can apply the probabilistic independence. Like if you know that A is independent of C and B given D, you can just cross this out. And now you made from a table which was the previous size, you made a table which is much, much smaller, right? It has only 2 variables. Again, if you know that probability B is independent of C given D, or is independent of D given C, whatever, then you can delete some more variables. And you will end up with a much smaller, if you sum the sizes of these tables, it will be typically, especially for large tables, much smaller than this table, right? But you can still compute any value, because any value in this table, you can just multiply these smaller tables and it will be the right value. Okay, and that's all the background we need for Bayesian networks. Bayesian networks are just implementing this idea, right? So it's a formal framework for compact representations of probabilities and inference over those probabilities. The idea is to do the same thing as we were doing with the full table, right? You can pick any variable, you can pick any evidence, and you can compute what is the probability of that variable given that evidence. And it consists of it's called a network, because there is a graph of variables. And then you have these arrows. And the arrows just means that there is some kind of direct influence between cavity and toothache, like between this variable and that variable. So the direct edge represents some kind of influence between parents and children. And the edges cannot create cycles, right? The edges always need to like go in that way that it will be directed acyclic graph, so it will not, like there can be cycles in the sense that there would be an undirected cycle, so you can have something like this, right? That's still fine, but you cannot have directed cycles. So this would be forbidden. So there is this graph which tells you what are the variables and what are the relationships, like basically where are some, it's a little more complex. It's not like if there is no edge, there is no influence, right? The edges are only some direct influence. And we will see that the edges are actually quite arbitrary in that problems. But for now, just you can think about them as causality, but they are not. And it's very important that they are not. But the first level intuition is all right. And then, like besides this graph, you need to have a set of conditional probability tables, right? So these are conditional probabilities, not joint probabilities anymore. And that's important because it is often on the test and people have it wrong. So for each node, you need a conditional probability table of variable in that node given the parents of that node. So in this example, what probability table will you have for this sketch node? It will be probability of catch given the parents of that node is the cavity. If there was this edge from the weather, what would be the probability you need in this node? Would be probability of toothache given weather and cavity. What probability would you have here in this node? Just the probability of cavity, yes. Right? So that's basically a network. That's all you need to know about it. No, like then you will have to like reason in it. But from the structure perspective, it's really just a set of nodes, some edges, and the edges are there only to define like which probability tables you have. Like they don't have any other real meaning, but if you put there the edge, you will need to get this probability table. Questions? Okay, so this is an example of a full probability table. It's a little lazy because it's showing only half of the probability table, right? It's taken from the book, that's why I chose it in this form, but there should be probability of non-B 0.999, right? And here there should be probability of non-E 0.998 and so on, right? So it's just to make it clearer, the picture, like the tables are only half of them. But it's always probability of the variable given the parents, and the story is simple. It's you have a cottage somewhere in the woods where you are not often there, and sometimes there is a burglary and somebody break into your cottage, and then you have an alarm for that. And if somebody breaks in, there is some probability that the alarm will start ringing. And then you have two friends. You have John and Mary, which have cottages somewhere nearby, and they're sometimes there and sometimes not. And if the alarm rings, then they'll pick up a phone and then they'll call you that something is wrong with your cottage, right? And there are sometimes little earthquakes, and the alarm can start ringing just because the earth has shaken and there is actually no burglary. And then you have associated probabilities, so burglaries happen once in 1,000 times, days, or whatever. Earthquakes happens twice as often as burglaries. And then you have some sensitivity of your alarm, and that's saying, again, like if there is a burglary and then there is an earthquake at the same time, then the probability that the alarm will be ringing is 95%. If there is a burglary and there is no earthquake, the alarm will be ringing with probability 94%. If there is no burglary and there is earthquake, the alarm will be on 29% of cases. And if there is no burglary or no earthquake, the alarm can still malfunction and ring in 1,000th of the cases, right? And if alarm is ringing, then John can hear it well and will call you with 90% probability. If the alarm is not ringing, there is 5% chance that like John's ears will be ringing, or they'll be ringing in John's ears, and he'll call you anyway that there is something wrong, even though it's not, right? Or some other cottage which you don't care about is ringing or something like that. And Mary probably lives a little farther, because if the, or is there less often at home, because if the alarm is ringing, she will call you only with 70% probability, and if the alarm is not ringing, she will call you with 1% probability. Does it make sense? Questions? So this is our model of the domain, right? If, as I was talking about reasoning, like reasoning is if you have some kind of model of the environment and you do some inference, you are trying to derive some new knowledge from the model that you were not aware of before. So this is already full Bayesian network with a graph and with a table. There is nothing more in the Bayesian network. Questions? Sure.
How exactly do we calculate the alarm ringing, like the 0.95%, for example? Do we calculate it, or we know it, and then we use it when calculating the if the alarm is ringing even for earthquake?
Yeah, so that's a very good question. Like all of these numbers are inputs from the perspective of Bayesian network, right? So how do you get that? You can either ask some experts and get their values, or you can have some measurements, right? So you can turn on the alarm and see, like intentionally turn on the alarm and see whether John calls, right? You will do it 100 times. John will be pissed, but you will get some idea about these numbers, right? For these prior probabilities, you can just like see some long-term average, right? Like how often in that area you have burglaries, how often you have earthquakes. For these, you would probably have to set up some kind of experiments, but Bayesian networks usually don't deal with that. Like they assume that these probability tables are the input, and then the question is how to compute different things which are not explicitly there. But yeah, that's a very, very good question. Thanks. That's the problem with the original distribution as well. Like, where do I get all those numbers? Like that would be insane. Okay. And how do the Bayesian networks represent joint probability distributions? We were talking about this chain rule, this kind of iterative application of the product rule. So if I want to have probability that John calls, Mary calls, alarm is ringing, burglary is happening, and earthquake is happening, then I can represent it using these tables, which are smaller. And from conditional independence, like if I know that some things are independent, if I know that whether John calls depends only on the alarm, right? He doesn't know whether Mary calls or not. It cannot depend on Mary. He doesn't know whether there is a burglary. Like he might know whether there is an earthquake, but let's assume that it's such a small earthquake that he wouldn't perceive it. So we could keep the earthquake, but we can cross at least these two for sure. If we cross even the last one, then this is what stays. Mary, let's say it also depends only on the alarm. Let's say we cannot cross out anything from there. We can cross out the earthquake because burglars don't care whether there is an earthquake and do their burglaries still if it's just a minor earthquake and the probability of the earthquake, right? So we have represented this large table using these small tables. That's what I was talking about before. And the smaller tables are what we have in the Bayesian network. So these independence, the things that I crossed out are the things which are not important enough to include in the model, and that's why we are saving the memory and compute we would need to take it into the account. Now, an interesting question, like can I always do this? Can I always use the chain rule to decompose the table? Right. What do I need to do it? I need there to be this kind of ordering so that all the arrows in the table always point only from the later variables to the earlier variables. Right? If I have that, I can represent the Bayesian network as this, and it works. I'm just taking into account some independence. But if it wasn't the case, right? If I needed to have an arrow from earlier to later, then this wouldn't work anymore. So why do you think we can do this? Why can we use this argument that any Bayesian network will be decomposed to this multiplication? Sounds like a problem you have probably solved in some basics of algorithmization or something. Yep. Exactly, right? So because it's directly classically graph, you know that there is a topological ordering, and the topological ordering is such an ordering of variables that the arrow always goes from lower number to higher number, or the other way around, you don't care, right? So once you find a topological ordering, that's the ordering you would put here. Then you know that this is always everything you need, because you always have just the variables of the higher number in the after the condition, and then if some of them are not there, that's fine, you will just cross them over. But you know that you can always rewrite the big table as the smaller tables if it's a directed acyclic graph. Perfect. Another thing, why for every table there is a Bayesian network which will represent it? Because you can include all of these edges, right? You can always include all of these edges, and it will still be directed acyclic graph. Okay, so that's Bayesian network. And now why did we do it? So that we can do the inference, right? So we can make the same computations as we were doing before with the full joint probability table, just with these smaller tables. So the general task is to compute a posterior probability distribution over a set of variables x, which we care about, which is the query, right? Which can be what is the probability that I have cavity, what is the probability that my cottage is being burglared. But it can be multiple variables as well, right? It can be a joint distribution, like I can care about A and B at the same time, right? I want the output to be the probability that A and B have all sorts of valuations. So that's the query X. Then I have some evidence. So for some of those variables, I know what is their value, right? So I know that the hook caught in the teeth, for example, or I know that it's raining, right? So for some of those variables, I have the valuation. That's this E, the evidence. And then we have Y, which are all the other variables in the domain I don't care about right now, right? I might not care about whether there was an earthquake or not. I just care about whether my cottage is under attack. So I just want to forget about that. I just want to marginalize it out, and that's this Y. Y are all the variables I just don't care about right now. And the goal is to compute this, right? To compute the probability of the variables that I care about, the joint distribution of the probabilities of the variables that I care about, given the evidence that is available. Now you can rewrite it using Bayes rule. So it's the probability of X and the evidence, given probability of the evidence. Since probability of the evidence is just a normalizer, very often we will just forget about that. And then we write it like this, that there is some alpha probability of X and E, the joint distribution. And we'll compute that as alpha times sum over all the values of the variables we don't care about, right? So we want to marginalize out everything in E and compute this. So this is already what is represented by the Bayesian network, right? This is the joint probability of all the variables. We want to sum over everything we don't care about, assign E that we know, and keep X's, which should be the output. And we can forget about the normalization and just normalize at the end. So if we take this example again, so X would be the burglary. Evidence would be whether Mary calls and whether John calls. And the things we don't care about right now is the alarm and earthquake, right? Like, we don't care whether the alarm is ringing or not. We care about the burglary. So from the previous, we want to compute the probability of burglary given John calls and Mary calls. Like, this evidence is that both of them were calling, right? The small letters are valuations. If I put them without negation, that means that they are positive, right? So burglary is the table. The capital letter is the whole random variable. So I care about both burglary true and false. And John is true and Mary is true. That's this on the left side. That equals to alpha times probability that it's burglary and John calls and Mary calls, like this John probability distribution. And we can compute that by summing over all the Y. So summing over the earthquake true false and alarm true false. This probability of burglary, John, Mary, earthquake, and alarm. And we can rewrite this joint table using the Bayesian network. So for burglary true, the small b, it will be like this. So the whole table was, how was that? So it was probability of burglary, probability of evidence were the top ones, probability of alarm given burglary and evidence times probability of John calls given alarm, probability of Mary calls given alarm, right? So I just substituted this full joint table with this product and put in the individual values. Here for the burglary, for the rest, this is the evidence we sum over where the earthquake happens. This is again what we sum over. This is the burglary, and this is the evidence. This is what we know that happened, right? Given the alarm and then Mary called given the alarm. Just algebra, just putting there what we wanted. And if we compute this for burglary true and for burglary false, and we normalize it, that's the result. Yes? Because we have it in the Bayesian network, right? The variable exists, And the earthquake influences the probability of the alarm, right? So we needed to have it in, we need to have it in that sum, but we don't care about, we don't want it in the output. But during the computation, we need to take into account, like, what happens if there is like alarm, and if there is not alarm? What happens if there is an earthquake, and what happens if there is no earthquake, right? Like, you have to consider all these combination in the computation, but then in the output, you don't care about it. Thank you. Any other questions? Right, so we can rewrite the inference in the full table just as inference in these smaller tables. And we saved space, right? Because we store the smaller tables. But did we save some computation? This way. Right? Like, if we had the full table, we could just apply this. We would have to sum over all the evidence for all values of the x, which we care about, right? Because we need to fill this, and then normalize. So we would still have to iterate over basically all fields in that table to compute it. You see it? So if we rewrite it, we save the space, but we would still have to make the computation. And that's why another thing which the Bayesian network is that if you have the independencies, you can rearrange the sum. So you see that probability of the burglary doesn't depend on earthquake or alarm, so you can just put it in front of the sums. Probability of earthquake naturally depends on whether the earthquake is happening or not, but it doesn't depend on the alarm, right? So you can put the earthquake in front of the alarm, and then already instead of making this like multiplication of 1, 2, 3, 4, 5 numbers for every possible combination of those variables you are summing through, you can make much less, just like multiply these 3, then multiply with this only once for each value, and then at the end only multiply once by this, right? So this way we have saved some computation. But that's not much. We can save even more if we think about how the computation progresses. So if we just draw, what would the, like, computing this sum do? You at the end multiply by the PB. Then for each value of PE, you will multiply by the value of PE. And for each of those, you will compute this sum. The sum will be over values of A. So it will be for A true and A false. And for each of them, you will compute the probability of John calls when there is alarm, and Mary calls when there is alarm, and John calls when there is no alarm, and John calls where there is no alarm. But even when you will compute the branch that there is no alarm, no evidence, no earthquake, again you will need to compute the probability that John calls when there is alarm, and probability that Mary calls when there is alarm, and probability John calls when there is no alarm, and probability there is Mary calls when there is no alarm, right? So if you look at the whole computation, this part and this part is exactly the same computation. this part and this part is exactly the same computation. Right? So if the whole problem is much, much larger, you will have like subtrees, the whole subtrees, which will be repeating there over and over again. So if you use dynamic programming, and if you cache these results of these computations, then you can do it just once. And when you find out that you need that combination of variables again, you will just query the cache, and you will save even more. Is the algorithm clear? This is an algorithm which for any query X and any evidence that you have will compute the joint distribution over the query. Like, if you have some evidence, what is the probability that that and that happens? And it will do it a little bit more efficiently than just working with the table itself, both in memory and in speed, but just a little bit more efficiently, right? Because inference in Bayesian network is still a hard problem. So in general, it's sharp P hard problem, which is an NP hard class, which is harder than NP complete. And in some special cases, so if the Bayesian network is a tree, a polytree just means that if you forget about the directions of the edges, that it will be a tree. So there are no cycles, not even the unrelated cycles. In that case, you can do it more efficiently, like fundamentally more efficiently. But otherwise, it's still exponential, right? So we saved a lot of computation. You probably already can work with tens of variables, especially if you assume a lot of independence, even if it's not there. If it's just like there is a weak dependence, you will assume it's independent. Then you can compute some tens of variables, but probably you cannot still scale to hundreds because it's still exponential. Okay. So that's the general theory of or an algorithm for Bayesian networks. Any questions for that? If not, I wanted to mention a couple of special Bayesian networks which you will probably encounter, but you might not even be taught that they are Bayesian networks. So one famous one which is used, for example, for the spam classification is called a naive bias classifier. And naive bias is because there is this assumption of all the variables are independent of each other. There is some class that you are trying to classify, like, for example, in the spam, whether it's a legitimate email which is called ham or spam. And you have a lot of observations, and every word is observation, right? Whether the word is there or isn't there is a new observation. And this is one very typical, like, supervised learning classifier, which is simple and quick, and that's why it's very often used. And it is a Bayesian network, basically. It says that there is an underlying hidden variable which you cannot observe, which is called, like, the class, which influences many other variables which you can observe, which are the words, right? So you can observe in the email whether there is a word or there isn't a word. And that's these things that you will compute. And it's very hard to compute, like, okay, if there is Viagra in my email, what is the probability that it is a spam? Right? You cannot, like, know this easily. But you can do the other way around. Like, how often does the word Viagra appear in spam emails and non-spam emails? Right? That sounds like an easy thing to compute. So that's why if this is the word, you can compute, like, if it's a spam, what is the probability? If it's not spam, what is the probability? That's the joint distribution you need here for this word. And for every word, you can compute that joint distribution. And the strong assumption you are making in naive bias is that there is no dependence between the words. Because in reality, you probably should have an edge from every other word as well, right? Because if it's a medical text, then if there is something about like erection, then there is very likely that there will be something about Viagra, right? If there is nothing about erection, then so if you find out that there is this one word in the document, it changes your probability that there is some other word in the document, right? Regardless of the class. So there is some dependence, but that would be too difficult to model. That's why the naivety and the naive bias is, okay, you forget about all these other relationships. You assume that there is only this relationship. You model it as this Bayesian network, and then you solve it. And this is how you solve it, right? Then if you just apply the same algorithm that we were talking about, you will take some alpha, which is the normalizer, probability of spam, which is the prior, and you will just multiply the probability of each word being there, probability that it is there in spam, and that's the probability of this email being spam, right? So you can use this whole framework, then the theory in Bayesian networks, to understand some details about this naive bias classifier. Another example is hidden Markov model. Hidden Markov model is again like a huge field of AI, which is again just a special Bayesian network you can think about, very often with continuous variables, but we can forget about it right now. And it is about dynamics. For example, for the robot example, if you have a robot, you have its true position, which is this hidden variable you cannot observe. Like where exactly it is, the robot just doesn't know. The robot just has different sensors, and based on those sensors, it will get some evidence, like the distance of the wall, the number of turns of the wheels, or something like that. And then the new position of the robot is again a hidden variable, depends on the previous position and the new evidence. And every round, you move to a new position and you get some new evidence. And again, it's much easier to compute what is the evidence, like what would be the observations, like you have a map, for example, and you ask, okay, if I am in this place, and I know how noisy my rangefinder is, like how far would I see the wall? And it's much easier to get than if I see the wall a meter in front of me, where I am, where am I, right? That's much more complex question. So if you have your like noise models, it's easy to say if you were somewhere, what would be your noisy observations, then the other way around. And if you have this, you can use, again, inference in Bayesian network to compute your position or the distribution over where your position could be. Okay. So that's all nice and pretty. Let's go to a little less pretty part. I told you that the edges in the network just means like what tables you want to provide. They actually don't mean anything in the real world. And that means that you can have this nice network, which we would say that kind of makes sense. But you can represent the very same Bayesian network using different networks, right? You can just have this. If you have conditional probability of earthquake given alarm and burglary, and conditional probability of alarm given John calls and Mary calls, then you can represent the very same Bayesian network, right? Like all the same data will be included. You will make the same inference. You will get the same observation, same results. Do you agree, or? Because it really just tells us what kind of data you give, and every single table is actually a direct consequence of the full joint probability table, right? So if you have the full joint probability table, you can compute all these tables, and it will compute them always the same way. So if you just use different smaller tables to represent the Bayesian network, it's still the same thing, right? There is nothing meaningful there. And Bayesian networks were actually developed by Judah Perl. who wanted to capture causality. Like he started doing that, and he was kind of unhappy with this result, that there is no meaning in those edges. You can rearrange the edges and everything still works. And that's why he continued working on it, and he kind of is considered to be founder of systematic understanding of causality. And he said, okay, we want to have the causality, and what does it mean, mainly? Right? Like everywhere in statistics, you learn that correlation is not causation, but you don't learn what is causation then, right? So since like the beginning of century, pretty much there is a systematic study of causality, where causality is a relationship between events where variable is actually caused by some other variable, like some consequences. For example, the cause needs to come before the effect, right? Like in the previous examples, like if you have just a random variable, like Mary calls, or if the alarm is caused by the earthquake, right? It cannot be causally like this. Like alarm cannot be cause of the earthquake, right? Even though the probability distribution might still work. And one interesting thing that it includes into the whole framework of causal networks now is this do operator. And that's a very fundamental thing to understand what is the difference between do x equals x and just observe x equal x, right? Because the Bayesian networks before that were just about observations. I could observe that there is an earthquake, and that changes the probability that there is an alarm. But I didn't cause the earthquake. I didn't cause the alarm. It just tells me how these variables are somehow connected, how knowing something about one tells me something about the other. It doesn't tell me that it is a cause. But this do operator is exactly the intervention operator, where I say, okay, now I can just turn on the alarm. I can remove all the other dependencies of the alarm, and I decide now to turn the alarm. That's a very different thing. It's something which, just by observations of the systems, you will never get. Right? You can see a million times that the alarm went on and John called, and you can compute these probabilities, but you cannot force it in Bayesian networks. And that's exactly the do operator. It's like, I don't care that alarm is caused by other things. Now I'm turning it on, regardless of anything. And that's the do operator. So do alarm is on will allow you to like think about it, to express this in the framework of the networks. And this is really a fundamental problem, which is really hard to explain in 10 minutes. But at least maybe I'll give you some spark of curiosity, and you will look at it more after. So there are 3 levels of causality or working with causality. Like the first level, which are Bayesian networks, is just association, it's just correlations. It cannot say, fundamentally cannot say anything about causality. It says just about correlations. If I see something happening, if I observe something happening, I know what is the probability that I would observe something else happening if I looked, right? That's the basic level, just associations. Second, fundamentally different level is intervention. Like if I actually can make the intervention, if I can change something, I can start understanding causality. That's the only way how I can be sure that something is cause of something else, that I force it. And that's why you know that we have randomized trials, like randomized clinical trials is one of those tools for this intervention, that you randomize over everything else, that helps you to remove dependency on anything else. And now you force treatment A or force treatment B. You do it using the do operator, and you observe the results. And if that, you can then find out that it causes or doesn't cause the output, right? And if you do it enough, you can start building this causal network. because some of this is a causal network. That is a Bayesian network where all the edges actually are causal, are meaning that one variable is causing the other variable. This is not, because if I do Mary calls, right? If I force Mary to call me, it will not influence the probability of alarm. But if I force the alarm, if I turn on the alarm without telling Mary, it will cause Mary calling me, right? So now, these networks are already not the same. One of them makes more sense than the other. So reasoning about the interventions and effects of the interventions and trying the interventions helps me to build this causal model or validate this causal model. And that allows me to get to the third level of causal reasoning, which is counterfactuals. Once I believe that I have the correct model of the world in the form of causal network, for example, then I can ask about things that didn't happen. Like, would I recover from my flu in 7 days if I didn't take this medication? Right? This is something that you can never do in the real world. You can never try it because you have just one option. You either take the medication or you don't take the medication. You cannot even try. You cannot even intervene to find out the counterfactual, the other option. But once you have the causal model, you can use it to compute these probabilities. But the causal model is always just a model. Like, you cannot prove that the model is correct. You can create consequences from the model and measure whether the consequences hold in the real world. But you will never be able to validate perfectly the model. So that's the kind of third level of causal reasoning, where once you have the model, you can ask these counterfactual questions. And the most current AI systems are still on the first level, right? If you think about ChatGPT, it didn't do any experiments when it was learning. It was just looking at the data on the internet. So it never had this ability to intervene. It could never do something and see what happens. It always just saw the correlation between things. So fundamentally, the thing just doesn't have any idea about causality, and there are papers in AI conferences showing that it doesn't do it, and then they are trying to add something like causal networks on top of it, something like causal models, to allow it to make this counterfactual reasoning. And that's a very active question, because many people believe that this is kind of the fundamental missing piece in AI, why they don't work so well, why they hallucinate, why you have all these problems, because it doesn't capture the causality, which is super important for us. And if you think about humans, how children learn, that's exactly what they do, right? They are playing with things, they are trying, if I do this, what happens? If I do that, what happens? They are not just observing the world. And it's very likely that if we were just observing the world all the time and we were not able to intervene, we would never be able to understand how it works because of this, because we wouldn't be able to build causal models, what we are somehow implicitly doing in our heads. Okay, super famous example, which relates to this. It's a well-known fact that there is a relationship between ice cream sales and shark attacks. If there are low sales of ice creams, then there are almost no shark attacks. If there is median sales of ice creams, there are decent amount of attacks. And if there is very, very high amount of ice cream sold, then there are the most shark attacks. So we can try to write it into a Bayesian network, right? So we will have two variables, shark attacks and ice cream sales. And now we know that there is a relationship. There's clear correlation between those, right? So how do I draw the arrow to make it a proper Bayesian network? So do I draw it like this, that ice cream causes the shark attacks because people are sweet and sharks like them more? Or the shark attacks make people stress, and that's why they crave sugar, and that's they'll get the much more ice cream, right? So Bayesian networks basically gives us these two options, and we can do both, and it will represent this table in an equivalent form in a Bayesian network, right? So which of them is better? Ice cream scores at X, yeah. Like, yes. So it's not the ice cream which is causing the attacks, right? There is some correlation between those, but there is another factor that is causing the attacks, and that's called like a common confounder. Right? If it's hot, people go to the beach and they eat ice cream and they get attacked by sharks, right? So if I just try to model it as a Bayesian network, I can do it always. I can always model any kind of joint distribution. But if I want to model it as a causal network, I might need to include some new variables which are called unobserved confounders. And I might need to find those so that they make sense, right? And if I make a network like this, it will still, like, it will be a larger network, which will have to capture, like, not much larger, right? But a little larger, that will have to capture the real logics, and then it is causal. And if I can, like, force the temperature, if I can kind of make artificial heaters around the beach, and I'll turn on the temperature, then I'll see the causal effects that the ice cream cells on the beach will go up and the attacks will go up. Right, so this is a very kind of canonical example everybody is using to show the difference between causation and correlation. And here I use it to like make clear that in the Bayesian networks, like, it is only about correlation. And you can make this step to this more complex theory of causal networks, where it is about causation, and you need to do these kind of things as searching for the confounders, as using the do operator to validate that your causal structure is correct. So as I said, like, this is for the whole course, the causality, but I just wanted to mention it because I think it's super important, and it will be super important for AI in the near future. If you want to read more about it, Judah Perl wrote a rather popular book about it, The Book of Why, which is like, before he was writing like very heavy math books on this, and this is popular book which you can just learn, like, read in the evenings or in a tram, and it explains both Bayesian networks a little bit, but then much more the causal networks. Okay, and the time is up, so I would just sum it up. Many AI problems require reasoning about uncertainty. If you want to make rational decisions, you need to know what outcomes you have and what probabilities these outcomes will have. Joint probability distribution is a powerful knowledge representation which allows you to reason about all those things, but it's super inefficient because it's exponential in the number of variables. That's why Bayesian networks invented, which are trying to reason about these distributions in a little more compact way, but they represent the distributions in smaller space, but the inference is still exponential, so you cannot hope to model really huge networks. But still, we were talking about an algorithm which is at least a little bit more efficient than going through all the options. And then you can specialize Bayesian networks to some special purposes and study them separately and use them more as like a theoretical framework. And very famous ones are naive Bayes classifier and hidden Markov models. And then if you really want to take into account causality, that's a whole different beast, which is somehow derived from this, but it was developing for another 20 years. And one thing to remember about it is that do operator and intervention is actually really crucial part of causality. Like, if you cannot interact with the world, if you can just observe it, then you cannot fundamentally learn about causality. And that's it. Questions? If no questions, then the next lecture will be about partially observable Markov decision processes. Then there will be a break because there is some shuffling of the schedule because of the holidays that were before, and we should see each other in 3 weeks, I guess. And I should be talking about generative AI in general.